topic of this conference is quantum spintronics. Some talks will be more quantum than the others. We encourage people to at least have the outlook towards quantum phenomena and kind of emphasize those. My talk will be coming from the classical side of things. So to me, that's kind of natural when I'm sort of venturing onto new things. First, I'd like to understand things on the classical front and then move towards the quantum things, and that's going to be the spirit of this talk. Spin superfluids is the main subject. Specifically, I will talk about the importance and the bad and good things about domain walls, phase slips, and skyrmions in the context of spin superfluids. My collaborators are listed here. Actually, some of them are in the audience. Sota K, who was my postdoc, now junior professor in New York, is here. Benedetta from Rambert Downers group in Utrecht is also here. Both of them, actually, all these three guys. Amir is supposed to be here, not yet, but all these three guys also give talks of their own. These two talks will be somewhat related to my talk. Sekwon and Hector are postdocs in my group who are doing all the work. Well, Rambert, you know. And Bert has also, of course, historically contributed a lot to this topic, and I'm thrilled that Bert is still interested in this subject. Because it's a tutorial, I will start with an introduction. The introduction will be idealized. Please it will touch upon idealized aspects, and feel free to interrupt me, but hopefully you're not going to interrupt me too much here because interesting things are going to be here. So hopefully we're going to get down to this topic, and that's going to be the technical part of my talk, really the interesting things which we're exploring these days. The inspiration naturally comes from the superfluidity and superconductivity, which are some of the most spectacular microscopic manifestations of quantum mechanics. Spin superfluids are analogs of these types of superfluids, not quite as perfect analogs as we'll see during my talk, but at least for starters, we can start thinking of spin superfluids as very similar. At least that's a natural way to start constructing our models and phenomenologies. And then as my talk progresses, I will drift away from the analogies to the superfluids and the superconductors and focus on the aspects which are unique to spin superfluids. And some of those will be bad, some of those will be good. And, some ugly, but that's in the eye of the beholder. Nevertheless, for starters, I will draw some knowledge from this phenomena, specifically with respect to hydrodynamic aspects, thermal and electrical controls. And in this talk, I will specifically focus on electrical controls. In Benedetta's talk, which will be the last talk of today, the focus will be on thermal aspects. And again, we'll proceed by analogy and then drift away. As an introductory slide, some basic summary of what we need to know about superfluidity at the most elementary level. So the superfluids are based on bosonic condensates. Typically, those are just bosonic particles or composite particles such as Cooper pairs, which generically at low temperatures tends to condense. In a sense, occupy the same single particle quantum state, loosely speaking. As a result of this condensation, the state of the system, the macroscopic state, can be described by a kind of wave function whose phase becomes the order parameter of the microscopic ordering and macroscopic dynamics. So upon the condensation, the basic degrees of freedom are the density of the particles and the condensate phase, rho and phi. So let us construct a simple theory in terms of those variables. The simplest Hamiltonian, gauge-invariant Hamiltonian that you would write down would have two pieces. C is compressibility associated with the particle density. Let me focus on a short-range interaction for now. So let me not worry about the electromagnetic phenomena in superconductors. So this could be a neutral superfluid. So C would be the local compressibility of a neutral superfluid. So that's a normal sort of elastic, think of it as elastic or hydrodynamic piece. And there is a stiffness associated with the condensate phase. Has to be expressed in terms of the gradient of the phase because of the gauge invariance. Apart from the Hamiltonian, we have to realize that these two variables are canonically conjugate because the particle density is the generator for phase shifts. So rho and phi are canonically conjugate. After constructing the Hamiltonian, the equations of motion, either classical, Hamilton's equations in the classical regime or Heisenberg equation in the quantum regime, can be immediately obtained from the conjugacy of rho and phi. And the two equations are this. The first one, which is derivative, time derivative of phi, which is given by the functional derivative of the Hamiltonian with respect to rho, is just the Josephson relation. And the similar equation for the dynamics of the density can be easily recognized as the continuity equation with this expression being the superflow current. The total particle density is conserved. Well, you can see that from the continuity equation, and that conservation law is rooted in the gauge symmetry. So these are the elementary basic building blocks of a superfluid, and we'll see some of them in a spin superfluid. However, unlike the gauge symmetry, which is pristine, we're going to be dealing with structural symmetries, which are necessarily approximate. And aspects related to that lack of a precise gauge-like symmetry really make the spin superfluidity distinct. In some sense less perfect, but in some other sense actually even more interesting. Okay, so what is a spin superfluid? Well, the condensate that we will start with is either an easy plane ferromagnet or an easy plane antiferromagnet. To get to an easy plane antiferromagnet, we can start with a Heisenberg antiferromagnet and subject it to an out-of-plane magnetic field. So then the Néel order goes into the xy plane, which is the easy plane for the Néel order dynamics, transfers to the external magnetic field. For the ferromagnet, we can start with a thin film of a ferromagnet with magnetostatic interactions naturally defined in the easy plane, or we could rely on some crystalline easy plane anisotropy. Then the two variables that we will focus on are the out-of-plane spin density and the azimuthal angle within of the order parameter dynamics within the easy plane. The order parameter is just the magnetization in the ferromantic case, and the Néel order in the antiferromantic case. The total spin of the system is canonically conjugate to the angle because spin is the generator of rotations. So this immediately follows. So if now we write the Hamiltonian in terms of out-of-plane spin density and the phase, again in this naturally coming out in the same form as the Hamiltonian for a superfluid on the previous slide, subject to the canonical conjugacy of spin and angle, we would anticipate the same equations of motion for rho, z, and for phi. Okay, so the equations are similar. We have a canonical conjugacy. We have similar Hamiltonian, so long as we have a rotational symmetry around the z axis. So that is, of course, necessarily an approximation. Okay, so again, just to emphasize, the quantity which will be transported through the system as a superfluid density is the out-of-plane spin. It's the actual out-of-plane spin in both ferromagnetic and antiferromagnetic cases. In fact, any XY model you would write down could be described like this. Okay. So in the magnetic case, the spin density corresponds to a tilt of the order parameter. In the antiferromagnetic case, this superfluid density corresponds to a relative canting of the two sublattices. So the order parameter is actually not tilted, it just stays in plane. Either way, the Hamiltonian is similar, and it's always the actual physical spin density out of plane that's been transported as a superfluid. Okay? In anything, ferromagnet, antiferromagnet, or you could imagine a spiral state with U1 symmetry breaking. So this is very general. So the assumption is that the key assumption is that we have rotational symmetry around the z-axis. So then spin along that, total spin along that direction is conserved quantity. And then because of these arguments, it would actually generally be transmitted as a superfluid. If you ask what magnons are doing, well, let's say in this case, magnons correspond to small angle fluctuations with respect to the order parameter that's in plane. So magnons actually would not be able to transport spin density out of plane in this case, with magnetization with order parameter strictly within the xy plane. Okay. So, yeah.
So that would be an effective description of some microscopic XXC model or something like that.
Yeah. Okay. Yeah. Oops. So, okay. Now this mode of spin transport nicely complements the other regimes of spin transport that are much more familiar. So let me summarize a few scenarios for spin transport, which should be familiar to people, at least in this audience. So we have a spin transport, a diffusive spin transport in metals, either normal or magnetic metals, carried by electrons. So charge current would be carried by electrons moving in the same direction of the opposite spin. Spin current corresponds to the electrons with opposite spin moving in the opposite directions. And that would carry a pure spin current, would be associated with a pure spin current. In a ferromagnetic metals or insulators, you could also carry spin by diffusive transport of magnons. So an individual magnon corresponds to tiny depolarization of the order parameter corresponding to angular momentum h bar opposite to the collective spin density. So it's just one species of particles that would carry heat as well as spin. The fact that it's one species actually has a lot of interesting consequences for thermoelectric properties. So the fact that it's just one particle, unlike one species, without without the whole counterpart, enhances thermal effects. Hence, the thermal effects, the spin-coelectronic effects, are very prominent in magnetic insulators associated with magnetic spin transport. But anyways, that's not the topic for my talk today. Then we have a spin transport carried by domain walls. Domain walls are relevant, again, still focusing on the simple case of rotational symmetry around the z-axis. Domain walls are relevant for easy axis anisotropy case. So in easy axis case, the ground state is either up or down along the easy axis, and then a topological excitation of that ground state would be a domain wall that separates the two domains. The spin out of plane total spin is still conserved, and as you can easily see, that total spin is proportional to the position of the domain wall. So x is proportional to the total spin, meaning that the position of the domain wall is canonically conjugate to the angle, to the azimuthal angle at the center of the domain wall, based on the same arguments as on the previous slide.
That is not the same scenario as you have shown before, because the canting is not necessarily near wall, isn't it?
No, this is again, on this slide, I'm just focusing on ferromagnets for simplicity. So this is my little table of different spin transport effects in ferromagnets. Let's say this is ferromagnetic metal, this is ferromagnetic insulator for simplicity, subject to rotational symmetry around the z-axis. And then we can, of course, start thinking what happens if you have some other type of order, or this rotational symmetry is broken, etc. But that's really a good starting point. I think it nicely summarizes different regimes of spin transport, which are really familiar to us by now. Finally, I think this is a natural this is a natural addition to these different regimes of spin transport pertaining to spin currents in ferromagnets with rotational symmetry on the z-axis in the easy plane case. So now we have the spin current density, which could be distributed, unlike in this case, which everything's kind of localized, all the interesting things localized to the vicinity of the main wall. Here, the spin current and dynamics could be distributed throughout the system, and they have a nice superfluid character, again, with the density of the spin current being conjugate to the density of the spin being conjugate to the local azimuthal angle. Okay, and the flux, local flux, is proportional to the gradient of this azimuthal angle. All right. Okay, so that's all nice, and there's nothing really. I'm not saying anything that new. So all of that has been understood since many years ago. What's relatively new are the tools, the experimental tools for injecting and detecting spin transport in these various different scenarios, the different regimes. So the two specific tools which I will be relying on in this talk are the spin torque and spin pumping, which describe transmission of spin current between a metal and a magnetic insulator, and the spin Hall, inverse spin Hall effect that could be used for converting spin and charge currents. So the charge current could be converted into transverse spin current, and vice versa. The spin current can be converted into charge current. So the spin Hall effect is now quite standard for inducing spin currents in the metals. Once these spin currents are induced, they can be sent through the whole structure, even an insulating heterostructure, using spin torque, spin pumping type of effects at interfaces. So this rely on just exchange interactions, and this type of effects allow for spin transfer from really different materials, even metallic and insulating, with the metallic and insulating materials. Spin Hall effect is what we routinely use these days to inject spin current into our structure in the first place. And then after spin current trickles through the entire system, possibly through a sequence of interfaces, makes turns or whatever, in the end we're going to measure the spin current, can measure by inverse spin Hall effect using another metal. You could also play similar games using heat fluxes, as Saito sensei has taught us over the last few years. So you could actually get rid of metals altogether and use insulators for injecting and ultimately detecting heat fluxes, with spin Seebeck effectively replacing a spin Hall. Okay. Oh, all right. So the simplest structure now that we can put together, and this will be the prototypical structure with respect to which I will propose experiments, and we'll really try to illustrate the spin superfluid behavior. The simplest structure looks like this, and it really puts together sort of more or less everything I've said so far. Namely, we're going to have a channel for spin superfluidity. Let us, for simplicity, assume that the channel is an easy plane ferromagnetic insulator. Maybe not the perfect superfluid because of dipolar effects, stray fields, etc. that Arne will touch upon. I will shove those under the rug completely for the purpose of my talk, because it's not really fundamental to the spin superfluids. You could also replace the ferromagnet with antiferromagnet, with a synthetic or natural antiferromagnet to mitigate those dipolar effects. I think Arne will probably touch upon those issues. But just for the sake of my discussion, to keep things simple, let me nevertheless assume that I have a ferromagnetic insulator. I will take into account things like shape anisotropy, but I will disregard long-range dipolar interactions, which could be a good approximation if the film is sufficiently thin. Then I have metals for injecting and detecting a spin current. On the left side, the injection happens via a combination of spin Hall and spin torque effects. So sending electrical current up, you induce a spin accumulation at the interface, which then exerts a spin transfer torque onto the magnetic insulator. That injects the spin current out of plane. It propagates as a superfluid through this channel, and then detected elsewhere by the reciprocal sequence of processes. Namely, the spin current will come out by via spin pumping, which is reciprocal to the torque, and then this spin pumping will inject a measurable voltage tangential to the interface via the inverse spin Hall effect. So that is the idea, and I think that's really the nicest, simplest. May not be experimentally most I don't know, relevant or exciting. Remains to be seen. But theoretically, this is somehow the nicest setup to try to think of the properties and various consequences of spin superfluidity. What happens at the interface, namely spin torque on one side and spin pumping on the other side, is analogous to Andreev reflection, which can also be seen from the expressions for the spin current flowing across the interface. So this is the simplified expression from the general theory projected onto the easy plane dynamics. So for the easy plane dynamics, within the xy plane, the out-of-plane projection of the spin current is given by the spin mixing conductance of the interface times the effective bias across the interface. That bias is the difference between the spin accumulation on the metal side and the frequency of collective precession on the insulating side. So it's just like an expression for the electrical current associated with Andreev reflection, where phi would stand for the phase of the superconducting order parameter, and mu s would be, instead of mu s, you would have twice the voltage on the normal metal side.
So can I ask a question?
Yeah.
This basically implies if you inject the spin current into the easy ferromagnetic insulator, you induce locally a phase shift.
You induce the phase dynamics. Yeah. So yeah, if you apply now initially this easy plane material, let's say, has a uniform order parameter within the plane, so uniform phase phi. The moment you apply the spin accumulation at this interface, the phase starts winding. You induce a texture. The texture is dynamic as well as well, it's a spatio-temporal texture. Right? There's a dynamic component and there's a spatial component to the texture. The dynamics eventually, upon reaching this interface, starts pumping the spin current. So that's the pumped expression for the pumped spin current on the detection side. On the detection side, we only have the dynamics. We don't have the spin accumulation. So that's, let's say, grounded. So that's just used as a detector. And the injection side, we have both mu sub s and the dynamics. Mu sub s is applied, and the dynamics has to be self-consistently worked out. If there are no losses, the losses in this insulator are described by Gilbert damping. If there are no losses, whatever spin current that you would inject at the left, proportional to this part, will partition equally. Half of it will be reflected back according to this pumping, and half of it will be transmitted across. And the net dynamics, frequency of the dynamics will be proportional to half of the spin accumulation. So this would be half. And, yeah, basically just corresponds to equal partitioning of the current if the structure is mirror symmetric. Mixing conductance can be calculated. So it's something that we have a really good microscopic and quantitative handle on. This is Landau-Budicke expression for the mixing conductance that was derived by Arne and co-workers back in 2000. And in this paper, we sort of put together reviewed the interplay of spin transfer and spin pumping effects, and various. At that point, we're focusing on metallic heterostructures, but now we're utilizing the same theory also for this type of heterostructures with insulators, specifically focusing on the superfluid transport, which happens once the spin current is injected. Okay, so the interfacial, the physics of what happens at the interface is the old physics. Is really what happens after the injection, which now bring some new aspects to the problem. Yeah.
So if you switch off the injection, does then your ferromagnet go back to its uniform ground state?
Yeah, that's because of Gilbert damping. Because of Gilbert damping. If you don't have Gilbert damping, yeah, then it will persist forever. But eventually it spirals down and goes back to the uniform state. So in the end of the day, you could think of the following effective circuit for what happens to spin flows in the system. We're injecting some spin current at the left interface, and the efficiency of that process is proportional to the mixing conductance of the left interface. That injected spin propagates towards the right interface, but some of it leaks away through the Gilbert damping. So alpha is the Gilbert damping, and the efficiency of that leakage, the conductance parameter associated with that leakage, is proportional to alpha and the length, full length of the channel that you have to traverse by the spin current. Ultimately, that has to exert mechanical torque on your substrate. Whatever hasn't leaked out will be detected on the right side. If there is no Gilbert damping, so if leakage is absent, then the spin current just goes through, and then it mimics precisely physics and dissipation as in NSN type of superconducting heterostructures. This leakage is really what makes it somehow different. Well, there are other aspects that have to do with additional isotropies. We're going to include those later. But for now, the new aspect, in addition to a perfect superfluid, is this dissipation, is this leakage of angular momentum. So it's like it's a superconductor that's a bit leaky. Okay.
Also super.
Well, it's it's super with respect to what magnons are doing. Okay. It's relative to magnons. It's all a matter of perspective. Relative to diffusion of magnons, which are leaking, well as don't propagate beyond the spin diffusion length. This is super. So in the context of spin transport, it's super. Of course, it's not as super as superconductors, but it can happen even at room temperature. So that room temperature aspect we get for free. Okay, and then we have to start worrying about dissipation and isotropies and things like that. Yeah.
You said we can make comments during the talk.
Yeah.
So my comment is simply, if you assume that is a very fundamental assumption, and the assumption you make is that alpha is independent of wave vector and energy. Then and only, which of course holds for the low energy magnons, or let's say the low wave vector. Probably does not hold for thermal magnons. But because basically you say that all the phononic system can be separated off, and then of course we have all.
Look, think of this as I'm starting from a clean slate, right? I'm building things up. So what you're saying is additional things. Sure, eventually, everything I say you can kind of go beyond. And what you're saying is that if we crank up the bias and the texture becomes sharper and sharper and sharper and sharper, at some point also this parameter alpha will depend on the texture. You really have to go to very, very sharp textures. Yeah, and realistically, I don't think, first of all, experimentally, I think the first struggle is even to get to this mode of spin transport. And in the linear response, the pitch of the texture would be as large as the whole, the size of your system. So you would not worry about this effect. And then as you crank up your bias, which is very challenging, will be very challenging to get to the regime. But eventually, yes. For very, very sharp textures, this parameter alpha will depend also on the texture, so will depend on the amount of the supercurrent that you're sending. For extremely sharp textures, maybe even the mixing conductance will start eventually depending on the current that you're sending through. But those are definitely not the things you would worry. What's that?
I have one more question about the supercurrent. I mean, suppose you don't have magnons, you just have a twisted spin configuration. Mm-hmm. Right, and according to your definition, there is still a supercurrent, right? Is this correct?
Yeah.
So my question is, what is moving?
Nothing has to move. I mean, that's the whole idea of supercurrent. It's a current that is associated with essentially equilibrium, a quasi-equilibrium state of the system. So but what's moving is that the question is at the boundaries. To maintain the twist, you have to somehow supply and eject the spin current at the boundaries. You have to maintain the torque. So we are maintaining that twist here by injecting a spin current via spin Hall effect and detecting spin current via pumping.
I mean, a sounding wave is also random.
Yeah, yeah, right. But still, I mean, so if you think about supercurrent, I mean, if you think about moving dipoles, they should generate an electric field, and this supercurrent doesn't, right?
Wow, it will generate an incredibly tiny field. It does, yeah. Yeah, I mean, if you really have to go to tiny, relativistic effects in the theory, but yeah, eventually, probably, yeah. Anyways, all right, so.
Can I also ask a question? The dissipation which happens here, does this have an analog in the superconducting?
No. No, because this has to do with microscopic, the processes which microscopically break this U1 symmetry. And there's nothing that breaks U1 symmetry.
Well, you know, if you have a critical current and I go above that.
That is something else. Yeah.
And if you have vortices, for example, which leads to
exactly. So those will add, yeah, the phase slips and things like that. Yeah, things like Landau criteria and phase slips. That physics adds on top. Yeah, and I'll touch upon some of those. The Landau criterion here simply is actually very easy to visualize. What happens is, which is ultimately very similar to Landau criterion and superfluids. But here, what happens is that as you're sending more and more spin current, you're twisting your texture more and more to the point that there will be a critical twist that it will energetically be preferable for the system to just completely come out of plane. So it's like when you're pressing onto some system and then it starts buckling. So it just comes out and just orders along the z-axis and completely cuts off the superfluid. Then you have a little bit of leftover of diffusion near the boundary, but the superfluid will be cut off. Okay. Let me now step through a bit quicker through the introductory slides. Because there are a few interesting things that I want to make sure that I touch upon that has to do with kind of really somehow exciting things. Not like, okay, we'll go by, so the starting point is not so exciting. Conceptually, we have some analogy, and it's not even such a good analogy. Okay, you know, and people start complaining. Okay, just some quick comments. Okay, well, we can also kind of improve our setup a little bit and separate the aspects that have to do with dynamics from the aspects that have to do with texture. So in the same structure like before, but now either sending a current in series like this or in parallel like this through our what used to be injection and detection side. So now we don't have injection detection side. Both sides work in concert. We can separate the dynamic and the texture aspects. So in this case, in this geometry, we're sending spin current from both sides, which will induce uniform dynamics, at least in the absence of Gilbert damping would be uniform dynamics. In this case, we would inject spin current on this side and extract it, the same amount of spin current on the right-hand side, which would induce static texture. So here we have a uniform dynamics, here we have static textures. So if you want to study phase slips, for example, you would go to this geometry, or Landau criterion, things like this. You would crank up the bias, and at some point, either you reach Landau criterion, and then the whole thing dies, or in linear response, you have phase slips, which will modify the magnetoresistance of the circuit. So that's kind of, that's the idea. Already in the linear response before this phase slips and Landau criterion aspects, the prediction is that you would measure different resistance in these two circuits, and the resistance would reflect the superfluid, the magnetoresistance would reflect the superfluid spin current in this direction. So in the static case, you don't have, the superfluid does not modify the resistance in your circuits. You would just measure ordinary platinum resistance, maybe subject to whatever, some proximity effect, magnetoresistance near the boundaries. And once you trigger the dynamics, the motive forces associated with the dynamics change the resistance, magnetoresistance that you would measure in the circuit. And that change of magnetoresistance would reflect the efficiency of your superfluid transport. In our theory, it's proportional to spin Hall angle squared, and divided the parameters. That has to do, you know, with the flow of spin supercurrent as described.
So Yaroslav,
yeah.
there is only a DC component of resistance that is induced, or there is also an AC component?
So I'm focusing in this talk on the DC part. Yeah, that's somehow the most remarkable, right? That you already have DC spin current through a system. Usually with magnets you think of like some kind of AC response, but with a superfluid you can maintain a DC spin current. But of course it's also interesting to think of AC, and in fact experimentally very useful to characterize the system. Then you pick up some features from the standing waves associated with the superfluid. This slide I don't have to dwell too much on because it will be a talk dedicated to this topic by So let me just leave it at that. All right. So so far it's been conceptual. Then you might, of course, you can ask all these questions. Okay, is it really interesting? Is it really so special? Who cares? And then my answer to that is, okay, let's just at least conceptually come up with a device, that you would just not be able to somehow dream up without these ideas of spin superfluidity. And at least on paper, it's a useful device by definition, by some definition of utility. So it's actually it's a spin transistor. Either a spin transistor or a domain wall register in which you're using a spin superfluid to move the domain walls. So just let's quickly go over it. And I really, somehow without thinking in terms of spin superfluidity, it would be extremely awkward, clumsy, to somehow understand how this device works. Okay, so in a nutshell, we have so it's a heterostructure in which we have a source that supplies spin accumulation, possibly as explained on the previous slides, or by some other means. And now we have a channel consisting of an easy axis for magnet on top and easy plane for magnet on the bottom. We have a domain, so the natural topological excitations are domain walls in the top channel and the superfluid in the bottom channel, and they're coupled by exchange. So what that means is that the domain wall would interrupt. If there's no domain wall, then the superfluid just goes through as before with this easy axis, just slightly renormalizing maybe parameters. Domain wall would interrupt the superfluid flow because it's an exchange interaction. Because then the phase of your superfluid would be locked, at least in linear response, to the phase, to the azimuthal angle and the center of the domain wall. So it interrupts the superflow. So if you try to inject the superflow, of course, the spin accumulation pumps spin current into the system. It propagates, it induces texture. If the superflow is interrupted, the texture will be static, but the spin current is still flowing. That spin current has to be absorbed by the domain wall because it has nowhere else to go. And you can actually work out microscopically all the torques, etc. Of course, it works out like that. It's, whatever supercurrent you inject, proportional to the mixing conductance and the spin accumulation, will be transmitted entirely into the domain wall. So you have now a means to carry spin current in a useful way over very long distances without actually any dissipation. This dissipation kicks in only once the domain wall starts moving. So it's a signal, really a non-dissipative signal that you transmit, and it only starts costing energy when things are moving and something useful is happening. Okay, so all right, then okay, it moves because if the spin current is absorbed by the domain wall, based on the arguments already touched upon it on the introductory slides, that domain wall will start sliding because the spin of the domain wall is proportional to the position. So if it injects a spin current, it moves. So it's a superfluid-induced domain wall motion. So that's kind of one application, or somehow thought Gedanken application. Another Gedanken application is a spin transistor. If you pin the position of this domain wall and pin the face of this domain wall, the superfluid will be interrupted up to some critical bias, up to some critical twist. Beyond that critical twist, the exchange coupling to the domain wall will not be strong enough to maintain the static angle, and then it's so similar to the Walker breakdown. So you kind of, as you crank up the bias, the angle between the as the middle, the orientation of the magnetization and the center domain wall and the superfluid increases to the point that this exchange coupling is not able to maintain or absorb the supercurrent, and then the magnetization below the domain wall depends, starts precessing, and superfluid just goes through and, in this very nonlinear fashion. So then, as a function of bias, the supercurrent you would detect on the right would be precisely 0, and then you have the jump. And the position of this jump can be controlled, for example, by the width of the domain wall, and that can be easily controlled by a voltage-induced magnetic anisotropy. So if you put an electrostatic gate here, it could precisely control the position of this jump. Below the jump, the spin current that goes through is precisely 0. Above the jump, you have a large spin current, because above this jump, the superfluid doesn't really care about the domain wall anymore. It just depends on and goes through. So okay, so I think this is a nice illustration that this idea is really useful and could be, once realized, could be immediately somehow exploited in possible devices. Yeah.
You just have an easy access. You don't have a hard access.
Yeah, so it's easy access in the top layer and hard access in the bottom layer. It's perfectly rotational invariant, yeah, and it's easy access and hard access, yeah. So easy access carries domain walls, and this will be like units of information, etc. We're going to use them for logic, and this easy plane is a conduit of spin current. And because of the innate nonlinear aspects, you could start designing transistors. So this is a spin transistor. So that's the idea. Okay. So now on to even somehow more interesting things. The most interesting things have to do with things which you think are bad, for starters. Namely, okay, everything is based now on a nice rotational symmetry on the z-axis. However, there will always be some sort of anisotropy within the z-axis that pins the phase. If the phase is pinned, there is no superfluidity. Right? So in linear response, you think anisotropy pins the phase, kills the superfluidity. And then you understand some ways to overcome it, but you really have to somehow pump the system very strongly to overcome this problem. So you will have, in linear response, the superfluid is pinned, but if you crank up the bias, at some point you can depin magnetization dynamics. But then you really should not think of it as a nice spiraling type of dynamics, but instead dynamics of domain walls. Okay? So domain walls are now becoming the natural excitations within the easy plane. So this is still the easy plane. I'm supposing there is some easy axis, parasitic easy axis in this direction. So this is top view of my easy plane. Now I have to think of domain wall dynamics. And this domain wall dynamics require, to induce this domain wall dynamics, that requires some critical threshold on my injection side. Once that critical threshold is reached, domain walls will move around, and you'll push them in. Once this train of domain walls that you push in reaches the detection side, the domain walls would unwind and induce a spin pumping signal, just like the superfluid. But the bad news is that you have to overcome, and in practice, if you make the estimate of how large this threshold you have to overcome, that's actually quite substantial, even for very weak anisotropies within the easy plane. Then we have a new, we came up with this new idea. Well, let's not overcome this threshold by applied bias. Let us overcome more naturally by thermal fluctuations. Let's crank up, let's design appropriate quasi-one-dimensional spin superfluids and crank up the temperature so that the domain walls are already present in a thermodynamic equilibrium just by thermal fluctuations. And then let's ask what happens to those, to the motion dynamics of the domain walls in the same experimental geometry as we've been using. Namely, we're going to apply, add contacts and then induce some spin accumulation of the contacts and measure the spin current, let's say, at the other contact. So what will happen? You have already domain walls present, so you don't have, in a sense, to overcome a large nonlinear threshold to inject them. So then two things, two essential elements that one has to recognize to understand, for understanding what really happens, and that actually is is in the end going to mimic the spin superfluid transporter. So one piece, a new piece that we recognized was that if a domain wall is injected by thermal fluctuations, so now in linear response, okay, I'm still applying very tiny bias at this contact, so not enough to start injecting domain walls just by this bias, but the domain walls are coming in and out by spontaneous thermal fluctuations. And if the domain wall is entering the system by a spontaneous thermal fluctuation that happens at some rate proportional to Boltzmann factor at the left interface, the spin accumulation does a work onto the domain wall that is proportional to its chirality. So I can calculate the work by integrating a torque over the dynamics at this boundary. So theta is just a three-dimensional angle. If I integrate the work, the torque over the angle to get the work, I get a nice crisp expression that depends only on the Q's chirality, plus or minus 1. So I have two types of left and right-handed domain walls. Right, chirality depends on the winding of the domain wall as I go from left to right within the easy plane, either clockwise or counterclockwise. So the work is proportional to the mixing conductance, the spin accumulation, so in the absence of spin accumulation there's nothing, and chirality. So what that means is that for one sign of spin accumulation, one chirality, the thermal barrier for injecting domain wall will be raised, for the opposite chirality will be lowered. So now the spin accumulation linear response acts as a stochastic source of domain walls of a given chirality. Okay? The chirality, so long as you have strong easy plane anisotropy, the chirality will be preserved. So long as we're below Landau criterion, so to say, we're not allowing magnetization to come out of plane, the chirality will be preserved. So whatever stochastic, whatever chirality we inject here stochastically, we'll have to diffuse across the system. And on the right-hand side, as this chirality exiting the system, it will pump current, just like a superfluid would pump the current, namely the pumped spin associated with one domain wall exiting the system on the right side, obtained by integrating the expression for the spin current, is just given again by the mixing conductance times the chirality. So this work couples to the chirality. Chirality can diffuse, it's conserved, and then as it exits the system, it gives back the spin current again in this nice, pristine fashion. So even though we don't have conservation of spin anymore, the chirality takes over the kind of the interesting collective superfluid-like dynamics. And the chirality is preserved, and that's just preserved much more robustly than the spin, because it does not rely on any symmetries. It just relies on the right energetics, namely that we have to have large enough easy plane anisotropy. All other parasitic anisotropies, now we don't really care. As long as we disallow this chirality to spontaneously unwind, those processes, again, that's a phase slips. So then we have to include phase slips on top of this physics. But then it's more like in a proper superconductor. OK, so let's just do some bookkeeping. Like I said, there are two types of chiralities. There are also there are four types of the domain walls in general: head-to-head, tail-to-tail of one chirality and the other chirality. I really don't care about head-to-tail, tail-to-tail, head-to-head aspect. I really just all I care about is chirality, because I'm coupling to the chirality and I'm detecting the chirality. All right. OK. So then we construct a transport theory for chirality. So forget about spin. Spin is no longer conserved. However, we still induce the dynamics of the chirality by spin accumulation at one contact, and we're still detecting spin coming out. So spin is still kind of good hydrodynamic quantity for injection and detection, and miraculously it couples to chirality. But in between, in our magnetic insulator, nothing is conserved except for chirality. And then we develop a transport theory for chirality. So we define a total called topological charge or chirality, which is the integral of the texture. The texture itself, gradient of the angle, is the density of the topological charge. Because it's conserved, we can derive the continuity equation. The most generic, simplest regime is diffusive, in which these domain walls move as Brownian particles. So then the current is given, the current of this chirality is given by diffusion coefficient times the gradient of the density rho. So rho is just this. Diffusion coefficient, take it as a phonological parameter. We can also calculate it from a stochastic LLG theory, which is given by this expression. Domain wall width, S is the spin density, alpha is Gilbert damping. So we still get 1 over Gilbert damping floating around, just like 1 over Gilbert damping in the denominator for the spin superfluid. But now it shows in the mobility or diffusion coefficient of the chirality. And then we have boundary conditions. That's the key. So we have a term for the chirality exiting the system. That's the boring. Well, the chirality that reaches the end, it just exits. But then we have a term for spontaneous injection of the domain walls. And that term will depend on the work. So for one chirality, this injection rate will be raised. For other chirality, it will be lowered according to the work by the spin accumulation. Okay? So that's the source. Plus minus stands for the two chiralities. So that's what the pumping, the source of the chirality come from this term. And then with these boundary conditions and with this theory, we can solve for the net spin current coming out on the detection side subject to the spin accumulation on the left. And naturally, we get something, we get very similar behavior to the spin superfluid. Namely, we get, as temperature increases, we would ultimately reach the limit for these non-local signals, like magnetic resistance, etc. in this geometry. We will ultimately reach what the spin superfluid, sort of idealized spin superfluid, predicts. Okay, so this is like a thermally activated superfluid in a sense, and it's kind of natural because the thermal fluctuations sort of restore U1 symmetry within the system, and eventually, when the temperature is large enough compared to the energy of a single domain wall, you don't really care. You shouldn't really care so much about this kind of parasitic anisotropies within the easy plane. Okay, so that's the idea. On top of it, of course, now there are bad things, which are phase slips. Phase slips are always bad. So phase slips here stand for unwinding of the chirality as the magnetization comes out of plane. But then you have a large energy barrier that you have to overcome. So long as we're in this temperature regime, so temperature is maybe comparable. That's the energy of a domain wall. Kappa is the parasitic easy axis anisotropy within the easy plane. But as long as temperature is much less with this energy scale, that's the cost of a phase slip, with this K standing for large easy plane anisotropy. So long as temperature is much less than easy plane anisotropy, then we're in business. So the bottom line, so long, we don't have to neglect all anisotropies. All we need is that the easy plane anisotropy is the strongest. So long as easy plane anisotropy is the strongest, we can design the regime in which the superfluid behavior would be restored, well, let's say by thermal fluctuations. So maybe you can come up with some other clever ideas. Okay, the phase slips, the two statements I can make about the phase slips. Okay, one thing is that they're bad, but the good statement is that they could be measured, which sort of is an interesting thing in its own right. And like I said, they could be measured in this geometry when you're sending electrical currents in parallel. Then the torques at the boundary try to induce a uniform superfluid carrying texture, and then the phase slips on top of that uniform texture would sort of propagate towards the boundaries, would result in a steady state dynamics of the magnetization at the boundaries. And associated with the dynamics at the boundaries, you have electromotive forces that reduce the resistance of the whole circuit. So a small reduction of the resistance in the circuit could be directly related to the phase slip rate. There is also quantum, so that's one of the quantum outlooks in this talk. You could also, in the exactly same geometry, you could study quantum phase slips. So far I have focused on thermally, stochastic of fluctuating aspects that have to do with thermal fluctuations. If you go to very low temperatures and quantum fluctuations take over, you can get quantum phase slips, which could be studied in exactly the same geometry, so exactly the same idea. Okay, so the last part, last couple slides that I want to touch upon, somehow coming from this superfluid point of view, eventually we don't really have a superfluid anymore. Instead, we have topological hydrodynamics. We have chiral domain walls which carry the information. I'm no longer describing. We ended up with some diffusive theory for chiral domain walls. So the main ingredients in them are really not superfluid dynamics in which we have some conservation law for spin density. Instead, we have a diffusive theory for topological charge. All we need is a means to couple to the topological charge, to inject it, and to detect that topological charge. Okay? So the easy plane systems, are not necessarily unique in this respect. So okay, let's go to other geometries, to other configurations in which we don't even have parent superfluid to start with. So this idea of topological hydrodynamics more general and even more interesting in a sense. So as an illustration of that, we went to a two-dimensional film with Skyrmans. Now, two-dimensional easy-access film with a little bit of Jelshinsky-Murray interaction to stabilize Skyrmans. Now we ask, well, no superfluid parent state whatsoever. And then we ask a question, well, can we somehow in a similar fashion inject those Skyrmans and detect the Skyrmans? And the answer is yes. So for starters, look, the Skyrmans are also conserved. So we start by developing continuity equation for the Skyrman. In terms of the quantity that is now being transported hydrodynamically is the Skyrman density. And the flux of the Skyrman density is this expression. Okay, so there's one more derivative, spatial derivative, compared to the expressions for the chirality. Okay, the chirality, the density of the chirality had one spatial derivative, and the current of the chirality had a temporal derivative. Now we have one additional spatial derivative. Okay, so two spatial derivatives here, and one temporal, one spatial derivative. So this is the Skyrman current. And that's the conserved Skyrman charge that we will try to send across the system. Well, first, a side remark that recently the Skyrmans at room temperature, this is the first experiment demonstrating, I think, presence of stable Skyrmans at room temperature, not just presence, but also a means to inject. So here, it's completely unrelated physics, but just to convince you that in principle a system with a bunch of Skyrmans is a meaningful, experimentally meaningful object. Let me show you this nice video. So here we have some magnetic film with the color here stands for magnetization out into the plane. So it's an easy access magnetic film, just like the film beneath here. In equilibrium, this kind of spaghetti-like domains with magnetization pointing, let's say, down, the gray up. You can move these objects by a spin Hall effect. And so if you apply an electrical current now across this through this constriction, that moves the spaghetti. In fact, the electrical current tries to push the spaghetti across this constriction. On the other side, as the spaghetti comes out, there are hydrodynamic instabilities, very much like instabilities blowing soap bubbles. So essentially, we're just blowing Skyrmans here like soap bubbles. Let me run this video. It's pretty cool. So the spaghetti is kind of pushed through, and the Skyrmans are spewing out. So now we want to do something like this, but somehow in a more controllable and scalable and useful geometry. So we want to spew the Skyrmans somehow by a metallic contact, and we're going to detect by reciprocal effect, utilizing these ideas of topological hydrodynamics. All we need for that is appropriate work that couples to Skyrman density, and this type of spin transfer torque that has one extra spatial derivative is exactly, if you work things out, exactly results in the work that is proportional to the flux of the Skerman density entering the system. So the total work, associated, let's say, with one Skerman is quantized, so Q is the total Skerman number, proportional to J is the electrical current, again, tangential to the interface. And then the detection is reciprocal to this torque. So the electromotive force on Zager reciprocal electromotive force is written like this. And then associated with Skermans coming out on the right side, this electromotive force is precisely proportional to the Skerman flux coming out. So we can use this torque and this electromotive force for injecting and detecting Skermans in an easy access ferromagnet. And we believe these ideas are very general. So we encourage people to kind of dream up their own regimes of topological hydrodynamics in which you have to choose the topological excitation somehow of interest and then figure out a way to couple to it with spintronic means. And now I have two examples by spin Hall effect and then this spin transfer torque via which we can couple to chirality in the first case and the Skerman density in the second case. And if you can couple, you can measure by reciprocal means. Okay, so that brings me to the end of my talk. I ran out of time, but that's because I was interrupted a lot. So, one more thing, organizational thing I forgot to mention. So the speaker from the previous talk will be the chair for the next talk. So I'll be chairing the next talk, etc. So it's nobody can stop me.
I can.
So I guess it's maybe time 1 minute for urgent questions.
I think there's been a lot of discussions, but maybe one last question.
The injection of the
Yeah. So the appropriate regime is such that you already have Skermans that are thermally activated, and then by the bias you just
Oh, so they were already present.
They have to be already present because the injection rate will be proportional to the Boltzmann factor, like either minus energy of the Skerman divided by temperature. Because if you want to do it in the linear response, of course you could just crank up the bias and start producing them. You have to overcome instability. So those are two ways. You can overcome instability even with respect to uniform material, but then you have to figure out how large the threshold bias is. Maybe too large. Maybe would just fry your sample. If you want to do it in the linear response, you have to be in the regime in which this topological excitation is already there, so that you know that the Boltzmann factor is not not too small, because the injection rate will be proportional to the same Boltzmann factor.
There are Skermians that can be driven in conductors, right? So
yeah, that video was actually a conductor.
Okay.
For a conductor.
So for you, whether it's an insulator or a conductor.
Yeah, I don't really care. Except with conduction, because it would be more difficult to measure because we're looking at drag effects, non-local magnetoroesistances. Like you'd have.
There would be a lot more.
Well, parasitic effects, but again, you could mitigate those with appropriate geometries.
But easier to move.
Yeah. But then what you measure is probably not so related. So it's easy to decipher from that.
Yeah, ultimately we're interested in antiferromagnets. Even though my talk was all on ferromagnets, we want antiferromagnets and insulators. Yeah.
To come back to another detail I was just mentioning, this is alpha. So you are interpreted correctly. If you have a constant alpha, this simply means you have no Mach-non or spin excitation phonon interaction in the system, because the background is just background.
Yeah, it's all lumped into alpha. So alpha is probably phononic, partially magnonic.
Yeah, but it's simply background, which you can.
It's some background. Yeah, featureless background.
No specific node coupling in this case.
No. Yeah. So this is just thermal background. Yeah, featureless. So of course, if like your type of systems, YIG with a lot of complications due to dipole interactions at low energies, but hopefully Arne will touch upon some of those issues. Like the physics at the low energy end of spectrum is really complicated, right?
Yours is also all low energy, correct?
What's that?
Yours is also low energy.
Yeah, but I'm focusing on this really simple regimes in which these dipolar effects are not playing a role.
Okay, let's move on to Arne.
Okay.
While Arne sets up.
Okay, but yeah, we'll chat during the coffee break. One quick thing: there's a conference in Brazil in May on this topic. So please.
It's organized in a workshop.
What's that?